Welcome to my video course on mastering ERTMS/ETCS signaling systems. If you've spent any time at all looking into modern railway operations, you've probably noticed that it can feel like drowning in an absolute alphabet soup of terminology. ETCS, RBC, OBU, EVC. Honestly, it can get pretty overwhelming. But don't worry, that is exactly what this explainer is for. Today, we're going to completely demystify these terms. By the end of this session, you'll be speaking the language of modern railway signaling fluently. To make sense of all this terminology, here's our game plan. 1. An introduction to ETCS. 2. Trackside subsystem equipment. 3. Train-borne subsystem components. And 4. Managing train movement. Section 1. Introduction to ETCS. Moving to a unified European system.
Section 2. Trackside subsystem equipment. The ground-based infrastructure.
The absolute biggest player on the ground is the RBC, or Radio Block Center. Think of the RBC as the ultimate traffic controller for a specific section of the railway. It calculates the exact position of every single train operating within its governance area, which, by the way, can be up to 70 kilometers long. It continuously talks to these trains using a dedicated mobile network called GSM-R. And just like a cellular network handing off your phone call as you drive down the highway, when a train approaches the edge of an RBC's territory, it performs a highly secure handover to the adjacent accepting RBC. That way, the train never actually loses supervision.
Working right alongside the RBC are the Eurobalises, which are typically arranged in Balise Groups. You've probably seen these yellow blocks mounted right between the rails. Notice the word passive in the description here? In ETCS Level 2, these balises are essentially electronic milestones. Because trains use internal sensors to measure the distance they've traveled, slight measurement errors can naturally build up over time. But as a train physically passes over a Eurobalise, the balise sends a precise fixed location message to the train, allowing the onboard systems to instantly correct any odometry errors. Pretty clever, right?
Section 3. Train-borne subsystem components. Inside the locomotive. Now that we're looking inside the cab, the overarching term you absolutely need to know is the OBU, the Onboard Unit. Now, this isn't just one single box. It's the comprehensive equipment suite installed on the train. As we know, ETCS moves safety responsibilities from the infrastructure right into the vehicle, making traditional physical trackside signals completely obsolete. Well, the OBU is the entire package of hardware and software that makes that massive shift possible. Let's look at the actual mechanics of how the train physically interacts with those trackside balises we just talked about. Remember how I said the fixed Eurobalises are passive? They literally don't even have their own power supply. So, as the train speeds over the balise, the OBU antenna unit beams down what's called a telepowering signal. This quick burst of electromagnetic energy actually wakes up the Eurobalise, which then instantly fires back its data telegram via an uplink signal right to the antenna. It is just an incredibly elegant solution for transmitting data at extremely high speeds. Deep inside the OBU sits the EVC, or the European Vital Computer. If the OBU is the body, the EVC is for sure the vital brain. It safely and continuously processes just an immense amount of data. It takes in the movement authorities from the RBC, reads the data telegrams picked up from the Eurobalises, processes the driver's inputs, and calculates the train's odometry from the wheel sensors. It crunches all of this to guarantee the train is operating within incredibly strict safety parameters. So you might be wondering, how does the driver actually see what the EVC is thinking? That happens through the DMI, the driver-machine interface. This is essentially the digital cockpit. Because there aren't any red or green lights outside the window anymore, the driver relies entirely on this monitor. It gives them all the crucial real-time data, the train's instantaneous speed on a digital tachometer, the target speed it needs to reach, the maximum permitted speed, and vital warning intervention times. It's the main line of communication between the human operator and the ETCS system. Section 4. Managing train movement. Operational rules and logic. Okay. Everything in ETCS revolves around the MA, the Movement Authority. Think of this as the fundamental digital permission slip a train needs to proceed. Without a valid MA, the train simply cannot move. It's a message sent straight from the trackside to the train-borne system, clearing the route ahead. And here's the crucial part. If a hazard is suddenly detected ahead, say a signal being replaced to danger, that movement authority can be instantly revoked, forcing the train to stop. Getting that permission slip isn't exactly simple, though. There's a very strict sequence required for the supervising RBC to actually issue a valid movement authority. Step 1, the RBC has to validate the exact position of the train and verify its specific characteristics. Step 2,
An internal, safe route must be created and assigned exclusively to that train by the interlocking system. And finally, step 3, only when those conditions are perfectly met is the specific movement authority packet actually transmitted over the radio network to the train.
Of course, conditions on a live railway aren't always perfect. And that brings us to the TSR, or Temporary Speed Restriction. This is exactly what it sounds like, a temporary speed limit enforced to safely manage hazards, like working staff on the tracks or infrastructure maintenance. To actually be valid in the system, a TSR absolutely must strictly define a starting point, an ending point, and the maximum allowed speed for that specific zone.
The system manages these restrictions in 2 distinct ways. On one side, we have predefined TSRs. These are planned way ahead of time during the engineering phase. They just sit dormant in the RBC's database until they're automatically triggered by a sensor, like a tunnel detector sensing an issue, for example. On the flip side, we have dynamic TSRs. These are introduced on the fly, in real time, by a human traffic controller at a control center to deal with sudden, unpredictable operational changes. Regardless of the type, both are instantly beamed to any approaching train.
Now, all of these data points, the movement authorities, the temporary speed restrictions, the permanent track speed limits, they all flow right into the onboard computer to generate the MRSP, which stands for the Most Restrictive Speed Profile. The crucial takeaway here is that the train is constantly looking ahead, layering all these various speed limits on top of each other, and strictly enforcing the lowest, most restrictive one. By continuously comparing the train's actual speed against this profile, the onboard computer dynamically calculates a completely safe braking curve. If the driver happens to get too close to that braking curve, the system escalates through a very strict series of MSRP limits. First, a pre-indication simply tells the driver a braking zone is coming up. If they don't slow down, they hit the indication limit, and then the warning limit, where an audible alarm will actually sound right in the cabin. Now, if the driver completely fails to obey the command to brake within a predefined time, the system takes over. It triggers a service brake intervention to automatically slow the train down, and if things are truly critical, it hits the final failsafe, an emergency brake intervention, bringing the train to a complete and immediate stop. It is a highly robust, multi-layered safety net.
From the RBCs routing traffic on the ground, all the way to the EVCs calculating braking curves in the cabin, ETCS is honestly a masterclass in automated, multi-layered safety. Thanks, we can see you next video.